In this video, I'm going to talk about benzene nomenclature and aromaticity property. Benzene and its derivatives, they are natural constituent of crude oils. The formula for benzene is C6H6 and it is a cyclic and fully conjugated compound. Nomenclature of benzene derivatives, it's very similar to the cycloalkane compounds. If you don't remember cycloalkane nomenclature, you can watch my video about nomenclature of that type of compound. But there is a little difference. There is a lot of benzene derivatives, they have common name. We need to memorize this name, and when we have nomenclature for benzene derivatives compound, we need to use that common name too. Here is the list of common names for some important benzene derivatives. The first compound is phenol. The second one is toluene. When we have two methyl group on benzene ring regardless of their positions, we call it xylene. This is aniline. This is anisole, benzoic acid. This is benzaldehyde. And the last one is cresol. So we need to memorize this name and use this name for nomenclature of aromatic compounds. For the first example, we put number 1 in order of the alphabet. So between bromo and chloro, bromine has priority because of the alphabets. And chlorine is 2, 3, 4, 5, 6. Then the name of its compound is 1 bromo, 2 chloro, benzene. For second example, we have phenol structure in our compound. So whenever we have a derivative of benzene that it has common name, we try to name this compound based on that common name. So in this case, the alphabet is not important anymore because we know this compound as a phenol, not as a benzene. So then always put number 1 for that functional group, that branch. It is important for our structure. Then number 2, number 3. So the name of this compound will be 3-bromophenol. Also in this example, we can see toluene structure. So we are going to name based on the toluene. So we need to put number 1 for this carbon because we named this compound based on the toluene. If we going to the left, we have a smaller number. We are closer to the substituent. So between chloro and nitro, we need to bring first chloro because of the alphabet. So 2 chloro, 5 nitro, toluene. Here is more example. Again, we can see benzoic acid. So we name this compound based on benzoic acid, and from here we have a smaller number. Then the name of this compound is 2-chlorobenzoic acid. For the second example, here we don't have common name for benzene derivative. So we need to put number based on the alphabet. This group is ethyl and this group is fluoro. So based on the alphabet, ethyl should be number 1, and then from the right side we will have a smaller number. 1 ethyl, 3 fluorobenzene. And for the last one, we have common name for this structure. When we have 2 methyl, the name of this compound will be xylene. We just said 1 and 4 xylene. It means those 2 methyl, they are on carbon 1 and 4. So instead of using number, we can use some prefix. When we have 2 groups on position of 1 and 2, like the first example here, we call it ortho. So instead of 2-chlorobenzoic acid, we can say ortho-chlorobenzoic acid. When we have 2 groups in position of 1 and 3, we call it meta. And for 1 and 4, we call it para. So we can just say paraxylene. So let's start to talk about the benzene property and explain what is the aromaticity. This is the structure for benzene, 6 carbon and 6 hydrogen. As you can see here, this structure has 3 double bonds and it is a conjugated compound. So we assume like alkene and like conjugated diene or triene, we can have electrophilic addition of compound on double bond, like addition of Br2 or HBr, but electrophilic addition reaction never happen for benzene ring. So we won't have these compounds, not only for bromine, but also for the other electrophile. This shows something is different for benzene structure. To understand better what is aromaticity, we would like to study the heat of hydrogenation for benzene and other type of compounds. I'm going to use cyclohexene as a reference, and we assume the energy for cyclohexane is 0. If we have cyclohexene and we react with hydrogen, produce cyclohexane, and it releases 118 kilojoules energy for us. What that means? It means cyclohexene, it has 118 kilojoule mole energy rather than cyclohexane. If we study cyclohexadiene for this reaction, the delta H for this reaction will be negative 230. So we have two double bonds, that's the reason the energy is higher. Actually, this amount is very close to 2 times 118, and the difference is because of the conjugation of these two double bond can make compound a little more stable. But for benzene, if we want to convert benzene to cyclohexane, the delta H is only 206. We expect to have 3 times 118. That is gonna be 356. But we can see 150 kilojoules difference. This big difference between the calculated energy and the actual energy is related to the aromaticity. Because the double bond for benzene, they are not localized. They are delocalized and they move inside of the ring. And this delocalization of the double bond make our compound very stable. Benzene is not the only aromatic compound. There is a lot of different type of aromatic compound. How we can find aromatic compound? There is an important rules that we call it Huckel's rules. Actually, to being aromatic, there is 3 main rules. Based on the Huckel rules, number of delocalized electron in our system should obey 4n plus 2, and n can be any integer number. If you put different number for n, we can have this number for aromatic compound 2, 6, 10, 14, and etc. So this number is aromatic numbers. But also Huckel's rule says if number of electrons above 4n electrons, our compound is anti-aromatic. There is 2 more rules that is very important. If those 2 rules imply for our structure, then we need to move to the Huckel rules. First, we need to have planar structure for our fully conjugated system. Put in another word, we should have 2D structure. The second rule is we need to have full conjugate system. Let's explain these rules by some example. Let us start with benzene that we already know it is aromatic. This is benzene structure. All carbon in benzene have sp2 hybridations. And we know sp2 is trigonal planar. So it is a 2D structure. We also know benzene has another resonance structure. So the electron, they can move in our system. So our system is fully conjugate. So rule 1 and rule 2 is implied for benzene. Then we need to count how many electrons do we have for our benzene ring. We have 3 pi bond. 3 pi bond, it means 6 electrons. 6 electron is belong to the aromatic compound. So it is aromatic. Let's have more example. At the first example, again, we have planar structure and all this carbon is sp2. And number of electron, we have 2 pi bonds, so we have 4 electron. 4 electron is belong to the 4n and it is anti-aromatic. This compound is cyclobutadiene. Next example is cyclooctatetraene. Exactly like the first example, we have a planar structure and we have 4 bonds, so 4 times 2, we have 8 electron. 8 pi electron is again belong to the 4n, so it is anti-aromatic. In this example, we don't have planar structure. We have a 3D structure for our compound. Then we don't count number of electron because one of those 2 rules, it doesn't apply for our structure. Then we just need to write non-aromatic. So let's look at these examples At the first one here, we have 4 electrons, but this carbon has 2 hydrogen and it is sp3. sp3 has tetrahedral structure, so it is 3D. So we don't have any planar molecule here. It's not only about planar, also we cannot have a fully conjugated system because the electron they cannot completely rotate in this structure. So whenever we have CH2 in our ring, we can say that compound is non-aromatic. But if we have positive or negative charge, then our system is planar and it can have complete resonance for the electron. Then for these two, we need to count how many electrons do we have. For first one, again, we have 4 electrons. 4 electrons is for anti-aromatic. And for the anion, we need to be careful. Whenever we have negative charge, it means we should count 2 electrons. If we have 1 electron, it would be radicals, like this structure. So this is 1 electron. But negative charge always is 1 lone pair. So we have 6 electrons here. So then this anion is aromatic. Sometimes instead of putting positive or negative charge on one carbon, they put in the ring. For example, instead of writing in this form, for these two compounds, you may see these ions in this form. We can follow a very simple formula to find how many electrons do we have if we have this kind of structure in any question. So number of electron is equals to number of carbon for your ring minus charge. Charge with its sign should be inside of the parentheses. Let's calculate for these two again. For the first example, we have 5 carbon minus, and the charge for the ring is positive 1. So the answer is 4 electrons. For the second one, again we have 5 carbon minus, but the charge is negative 1. We know negative will be positive. So the answer is 6 electrons. So let's have more example. Whenever we see the structure with hybrid resonance form, we don't need to go to evaluate those two rules. So we know this structure is planar and also it has fully conjugation resonance. The first ring has 7 carbon. 7 minus positive 1, it has 6 electrons. So it is aromatic. The second one has 4 carbon minus charge, again is 6 electrons. So it is aromatic. The last one has more than one ring, but it really doesn't matter. We can count the electrons. 2, 4, 6, 8, 10. We have 10 electrons. Keep in mind again, we don't count bond, we count electrons. 10 electron again is belong to the aromatic. The aromatic compound, they are very stable rather than the non-aromatic compound, and anti-aromatic, they are unstable. We have also aromaticity in heterocyclic compound. Heterocyclic compound, they are cyclic compound that in addition of carbon on that ring, they have other atoms like oxygen, nitrogen, and so on. Here is some example for heterocyclic compound. This is pyrrole, this is furane, and this is pyridine. To calculate number of electron in heterocyclic compound, there is a very simple rule. Look at your heteroatoms. If it has double bond, that heteroatom, like pyridine, don't count this electron for the ring. But if it doesn't have double bond, so here oxygen doesn't have any double bond, or here in pyrrole, nitrogen doesn't have double bond, then count only one of these lone pair. If you look at here, in pyrrole, we have 2 pi bond, it is 4 electron, plus 2 lone pair electron. It's going to be 6 electrons, so it is aromatic. In furane, we have 2, 4, 6 electron, again it's aromatic. For pyridine, we have 3 bond, we don't count that lone pair. Then again we have 6 electron and it is aromatic. If I want to draw the structure for pyridine, if this is pi orbitals for pyridine, I show interaction by red. This is 3 pi bond. Then lone pair for pyridine, it is here. It is perpendicular to the plane of the pi bond. So it cannot have resonance with this system. So we cannot calculate this electron for the ring. But if we don't have pi bond for that atoms, then lone pair can be parallel with a pi system, and it can have resonance with this pi system, and then this electron play the role in aromaticity of the system. Let's have more example. This compound is indole. We have 1, 2, 3, 4 pi. 4 pi is means 8 electron. Also we have 2 electron for nitrogen, then it's going to be 10 electron. 10 electron is aromatic. The name of this compound is thiophene. Again we have 2, 4, and we count only one of these lone pair. So we have 6 electron and it is aromatic. Having boron in the cyclic system is a little tricky. We need to be careful because we know boron has a vacant orbital, and always we need to know there is electron pair even if it doesn't show in the structure. So there is another resonance form for this structure. I'm going to show it here. So this system right now has 6 electrons and it is aromatic. Here is another example. Each pair of nitrogen and boron, they can have a Lewis acid-base reaction and make 3 pi bond in our system. And this is another resonance form for our molecule. It is exactly like benzene. All boron is negative and all nitrogen is positive. So it is like benzene, but it is not organic compound because we don't have any carbon here. In some textbooks, they call it inorganic benzene. And the last examples is this compound. We have 2, 4, and 6 electrons. But we cannot say this compound is aromatic because again we have CH2 in our structure. So this CH2, it avoids to have a fully conjugated system, and also we don't have the planar structure. So this compound is just non-aromatic compound. To watching more video, please subscribe our YouTube channel.